Hello friends, welcome back to the channel. So far we have been accessing everything in our Kubernetes cluster without any restrictions. But in real world scenarios, that's not how things work. In real organizations, a Kubernetes cluster will have multiple nodes, multiple namespaces, deployments, replica sets, pods, services, and most commonly multiple users accessing the cluster. Now imagine this. If everyone has full access, anyone could accidentally delete resources, modify someone else's application, or even expose sensitive data like secrets. That's risky, right? So, in real environments, we must enforce restrictions on who can access what and what actions they can perform. And this is exactly where RBAC, role-based access control, comes into the picture. Now, why do we need RBAC? Let's understand this with a simple real-time example. Suppose we have a user named INT-SEH viewer. Now here INT stands for integration, SEH is our organization's abbreviation. Viewer means this user has read-only access. This is just a naming convention that we are following in our project. You can name your users anything based on your organization standards. Now imagine this user logs into the Kubernetes cluster. What should this user be able to do? This user should be able to check the pod status and view logs. And what this user should not be allowed to do? This user should not be allowed to create resources, view secrets, or modify role bindings or any RBAC configurations. Similarly, developers should deploy applications only in specific namespaces. DevOps teams may have broader access. Infra teams may have read-only access. Admin should have full control. So access is controlled based on rules. Before we jump into RBAC, we need to understand two key concepts: authentication and authorization. Authentication means who you are. In any system, whether it is Kubernetes, Jenkins, AWS, Bitbucket, the first step is always authentication. This means you are providing that you are a valid user. You can do this using credentials like username or password, tokens, certificates, etc. In real organization, this is usually integrated with LDAP or Active Directory. If authentication fails, you get 401 unauthorized error, and if successful, you get 200 OK. Now, just because you are authenticated, it doesn't mean you can access everything. After authentication, the system checks, are you allowed to perform this action? This is called authorization. For example, can you create a pod? Can you delete a deployment? Can you view secrets, etc. Again, if not allowed, you will be thrown 403 forbidden error. If allowed, action succeeds and a 200 OK status will be given. Now let's understand this authentication and authorization with Jenkins, which almost every organization uses. Suppose we have a user named Riya Joshi. The first step is authentication. Riya logs into Jenkins user with her credentials. If credentials are correct, she gets access, means 200 OK status. If wrong, she gets 401 unauthorized error. Now next step is authorization. Now Riya is logged in and she can trigger a job, which means 200 OK, but she cannot see a job configuration. Why? Because her role does not allow that action. So login success means authentication, permission check means authorization. If she tries to access something restricted, 403 forbidden error occurs. So authentication checks who you are and authorization checks what can you do. Both are required to securely access any system. Now, before we jump deeper into RBAC, there is one important thing we need to understand. There are different authorization models available to control access in systems like Kubernetes. For example, role-based access control, RBAC, attribute-based access control, ABAC, node authorization specific to Kubernetes only. Out of all these, RBAC is the most commonly used and widely adopted model. So RBAC stands for role-based access control. In simple terms, RBAC determines whether a user is allowed to perform a certain action on a resource based on the role assigned to them. So instead of giving permissions directly to users, we assign roles, and the roles define what actions are allowed. Now let's understand with a simple example. Let's say in our organization, we have different roles like DevOps. And if you are part of this DevOps team, you can create resource, you can read them, and you can update them. Similarly, you have monitoring team, And if you are part of monitoring team, you can only view resources, read only access. And if you are an admin team, you can do everything, full control over the cluster. So what's happening here? We are controlling access based on roles, not individual users. And that's the power of RBAC, role-based access control. Now, to start understanding how role-based access control works in Kubernetes, the first thing we need is a user. But here is something very important. Kubernetes does not have the concept of users internally. We cannot create a user in Kubernetes like how we create pods, deployments, services, etc. There is no command like kubectl create user. That simply does not exist in Kubernetes. Then what is a user in Kubernetes? In Kubernetes, a user or a group is just an arbitrary string. That's it. It could be a username like John, a user ID like int/viewer, or even a group name. Kubernetes does not store or manage users. It just trusts whatever identity is provided during authentication. Now let's actually see how this works practically. Well, this is my Kubernetes cluster. When we create a cluster using kubeadm, all the cluster related information is stored in a file called .kube.config. Let's open this file. Here you can see multiple sections. The first one is cluster section. This contains information about clusters. In our case, Kubernetes is the default kubeadm cluster. But in real scenarios, you can have multiple clusters like AWS EKS, Azure AKS, etc. And you can switch between them. Here we have user section. Now this is very interesting. When we create a kubeadm cluster, a default user called Kubernetes-admin is automatically created. This is the user we have been using so far to access the cluster and perform all operations. That's why till now we had full access without restrictions. Next we have context section. A context is a combination of cluster, user, default namespace. For example, Kubernetes-admin @Kubernetes. This means user Kubernetes admin and Kubernetes is the cluster name and namespace here is default. And this is our current context. Next, certificates. Now you will also see fields like certificate authority data, client certificate data, and client key data. These are used for authentication. Now let's understand the core concept. In traditional Kubernetes, authentication is done using certificates. Kubernetes only trusts certificates that are signed by its own CA, certificate authority. Where are these certificates stored? On the master node, certificates are present in /etc/kubernetes/pki. Let's go there. You will find multiple certificate files like ca.crt, ca.key, API server.crt, etc. Kubernetes will only authenticate a user if the user presents a certificate that is signed by this certificate authority ca.crt. So when we say create a user in Kubernetes, we are not actually creating a user inside Kubernetes. Instead, we are generating a certificate and using that certificate as the identity of the user. So in the next step, we will generate a certificate for our user, configure it in kubeconfig, and then use it to access the cluster. And after that, we will apply RBAC roles and bindings to control what this user can do. Alright, now let's move to the most important hands-on part. Now let's generate the certificate for our user. In this step first, we need to generate a private key for the user using OpenSSL. Before that, let me move to the code repo, that is /opt code repo and my Kubernetes playlist. So here we will generate our key. To run this command, OpenSSL genrsa-out int/viewer.key 2048. Let me explain what we are doing here. We are using OpenSSL genrsa to generate an RSA private key, -out int/viewer.key storing the key in a file, and 2048 key size, standard secure size. Now let's verify using ls-lart. So int sch viewer.key file being generated. So our private key is successfully generated. Next, generate certificate signing request. We need to create a certificate signing request for the user. This CSR will be sent to Kubernetes CA for signing. For that, we will need to run OpenSSL req request command. Now let's understand this command properly. Here -new creating a new CSR. -key using the private key we generated. -out output file, that is certificate signing request file. Now very important part, -subject is equal to cn int sch viewer /o Kubernetes namespace admin. So here cn common name acts as the username. Here it is int sch viewer. -o organization acts as the group name. Here it is Kubernetes namespace admin. And we are storing the CSR in the current location, that is /opt/code repo/Kubernetes playlist. Now hit enter. Now let's verify using ll command. Now you can see we have private key and certificate signing request. But this CSR is still not useful until it is signed by a trusted certificate authority, CA. What is the Kubernetes CA? In a KubeADM cluster, the certificate authority details are in /etc/Kubernetes/PKI. Now here you can see very important files, ca.crt and ca.key. ca.crt, this is the CA certificate, and ca.key, this is the CA private key. Kubernetes will only trust certificates that are signed by this ca.crt plus ca.key. So now we are going to sign our CSR using this CA. To sign the CSR, we need to run OpenSSL command. Let's understand this command. Here -req indicates this is a CSR. -in input CSR file. -ca/etc/Kubernetes/PKI/ca.crt. This is CA certificate. -ca key is ca.key, that is inside /etc/Kubernetes/PKI. -out, this is output certificate file, and -days 365 certificate validity, that is 1 year. Hit enter. So here basically we are saying Kubernetes CA, please sign the CSR and generate a valid certificate for this user. Now the certificate is generated. If we run ll, we can see int sch viewer.key, this is a private key. int sch viewer.csr, this is certificate signing request, and int sch viewer.crt, this is signed certificate. Now this is the moment our user int sch viewer is now authenticated. Why? Because this certificate is signed by Kubernetes CA and Kubernetes trusts it. Alright, now we have successfully generated the certificate for our user. Next step is to add this user to the cluster configuration. We will use kubectl config set credentials command. What are we doing here? Here int sch viewer.crt, this is the certificate we generated. int sch viewer.key, this is the private key. So we are basically telling Kubernetes this is a valid user and here are the credentials to authenticate. Hit enter. You should see user int sch viewer set. Now let's verify. Just do cat to .kube/config file. Hit enter. Here under users, you can see int sch viewer user has been added, and the client certificate location and the client key location is also available here. It means the user is now added to the kubeconfig file. Now we need to create the context. So what exactly a context? A context is basically a connection profile. It tells Kubernetes which cluster to talk to, which user to use, and which namespace to operate. Instead of typing all these details every time, we bundle them together into one name, and that name is the context. For that we will run kubectl config set context command. When we run this command, what we are saying here, create a new context named int-ser-kubernetes, and inside this context use the cluster called Kubernetes, authenticate as the user int-ser, and by default work in the default namespace. So this one line is basically tying three things together: cluster, user, namespace, and giving it a single name int-ser-kubernetes. Once I hit enter, Kubernetes confirms it by saying context int-ser-kubernetes created. That means the configuration is now saved inside the kubeconfig file. Now let's verify what actually happened behind the scene. So when I open kubeconfig file again, under context, you will see a new block has been added. So this block is actual representation of the context we just created. Here name field int-ser-kubernetes is just a label. It is what we will use later when we switch context. Inside the context section, this cluster Kubernetes means this context will connect to the Kubernetes cluster named Kubernetes. User int-ser means it will use the credentials of this user to authenticate. Namespace default means by default all commands will run in the default namespace unless we override it. Now that we have created our context, let's actually see all the contexts available in our system. So I will run kubectl config get context command. Now this command will list all the contexts configured in our kubeconfig file. So if I hit enter, so you will see a table like this. This table is showing all the connection profiles, all the contexts we have created. The most important thing here is this star symbol. This star indicates the currently active context. Right now the star is on Kubernetes admin @Kubernetes. That means currently all the kubectl commands we run are using the admin user connected to the Kubernetes cluster and working in the default namespace. So basically right now we are acting as an admin user. Now let's switch to the new context that we just created, that is int-ser-kubernetes. So I will run kubectl config use context and then context name. Hit enter. As soon as I hit enter, I get switched to context int-ser-kubernetes. So now Kubernetes has changed our identity. We are no longer acting as admin. Now we are acting as int-ser user. Let's verify this again. If I do kubectl config get context again, now the output will look like this. Now observe it carefully. This star has moved to int-ser Kubernetes. That means this is now our active context and we are now operating as the int-ser user. Now comes the most interesting part. Let's try to access the cluster. I will run a very simple command, that is kubectl get pods, hit enter, and boom, you will get an error like error from server, pods is forbidden. User int-ser cannot list resource pods in the API group in the namespace default. Now this is where the real learning happens. What does happen here? First thing, our user is successfully authenticated. How do we know that? Because the server recognized the user int-ser. So the certificate and identity are valid, but the user is not authorized. That means Kubernetes knows who you are, but it is not allowing you to do anything. And that's why we are getting this 403 forbidden error. So this is the key concept you need to understand. Authentication means who you are. Authorization means what you are allowed to do. Right now, authentication is working, but authorization is missing. You can think of this user as a skeleton user. It exists, it is valid, but it has zero permissions. That's exactly why we need RBAC, role-based access control, which we will configure next to give proper access. Now before moving ahead, let's switch back to our admin user. For that, kubectl config use context and this default admin context. And you will see switch to context kubernetes-admin@kubernetes. Now we are back to the admin context, and this user has full access to the cluster. So now we are ready to configure permissions for our new user. Now let's actually give permissions to our user int-sh viewer. In Kubernetes, permissions are not given directly to users. Instead, we use roles and RoleBindings to control access. So what I will do is, I will take you to my IDE. Here I have my repository which is in my Kubernetes playlist repo. And it is already checked into GitHub. Inside this repo, I have created a file called shrole.yaml under day18 RBAC folder. Now let's start writing the role. So just like any other Kubernetes resource, a role also has a basic structure. We define API version, kind, metadata, and then rules instead of spec. Now if you are not sure about the API version, you can always verify from the cluster. Let me quickly show you. In the cluster, if I run kubectl API resources pipe-grep roles and hit enter, you can see roles API version is rbac.authorization.kubernetes.io/v1. Also notice this column true. This is for namespaced. Namespaced is equal to true for roles. That means role is a namespace level resource, not cluster wide. So now let's write our YAML. API version rbac.authorization.kubernetes.io, kind is role. In metadata, let's give it a name. I am giving this role a meaningful name, that is SEH pod reader. From the name itself, we understand that this role will only allow reading pod related data. Now comes the most important part, defining the rules. Let's understand this properly. First we have API groups. Now this tells Kubernetes which API group we are targeting. For pods, the API version is v1. Whenever you see API version is v1, it means it belongs to the core Kubernetes API group. And the core API group is represented by an empty string. Now, if you compare this with something like deployments, in deployments, the API version is apps/v1, which means API group is apps here. So in that case, we would write apps here instead of empty string. This distinction is very important because different API groups can have similar resource names. Now we define resources. Here we are saying resources, pods and pod logs. That means access to pods and access to pod logs. Now comes verbs. Verbs define what actions are allowed. If you are not sure what verbs are available, you can always check from the cluster. Let me show you that. I will go to terminal and run kubectl API resources -o void pipe-grep pod. If I hit enter, for pods you can see all the supported actions like create, delete collection, get, list, patch, update, watch. But for our use case, we only want read-only access, so we are giving get, list, watch, which means get, fetch a single pod, list all pods, watch, continuously monitor changes. So now what does this role actually do? Any user who gets this role will be able to view pods, list pods, watch pod changes and see logs, and they will not be able to create pods, delete pods, modify anything. So this becomes our final role manifest. Now since I am maintaining everything in Git, I will go ahead and check this file into my repository using git commands. For that I will use git add dot git commit -m sch manifest file created and then git push. So now this role definition is version controlled and pushed to GitHub. So on my Kubernetes master node, I already have this repository cloned under /opt/code repo. Since I just pushed my role YAML to GitHub, I will pull the latest changes using git pull command. So now my local repo is updated with the latest manifest. If I do ls, I can see day18 folder. If I do ls day18, my file is available here. Next, I will apply this role into the cluster using kubectl apply command. And you will see the output role sh pod reader created. That means Kubernetes has successfully created this role. Now let's verify it using kubectl get roles command. And here we should be able to see our role, that is sh pod reader. Now one very important thing to understand here is roles are namespaced resources. So whenever you create a role, it gets created inside a specific namespace. If you are not sure which namespace you are currently working in, you can check it like this. kubectl config view --minify pipe grep namespace. Hit enter. This will show you the active namespace. In our case, it is default. So that means our role sh pod reader is created inside the default namespace. Now let's pause here and understand where we are. We have created a user, we have created a role, but still the user does not have any permissions. Why? Because Kubernetes does not automatically connect users to roles. So now we need a way to link the user and the role, and that is done using role binding. Think of it like this: role defines what actions are allowed. Subject or user defines who is getting access, and role binding connects both. So role binding is basically the bridge between user and permissions. Now in role binding, we define something called a subject. Subject can be a user, a group, or a service account. In our case, the subject is our user, that is int_sh viewer, and we want to give this user permission to read pods, which is defined in our role sh pod reader. Now let me take you back to the repo. We will create another file sh RoleBinding.yaml. Before writing the YAML, let's verify the API version and kind. I will run kubectl API resources pipe grep RoleBinding. Hit enter. And you will see something like this: RoleBindings RBAC.authorization.kubernetes.io/v1. So this is the API version for RoleBindings, and true means it is namespaced. And the same for cluster RoleBinding, the same API, but namespaced is equal to false. Now that is very important. RoleBinding is namespaced, but cluster RoleBinding is not namespaced. What does that mean? RoleBinding gives access within a specific namespace only. Cluster RoleBinding gives access across the entire cluster. So in our case, since we want to give access only in a default namespace, we will use RoleBinding. So just remember this line: RoleBinding namespace level access, cluster RoleBinding cluster wide access. Now since we only want our user to read pods in the default namespace, RoleBinding is the correct choice. Now I will go back to my IDE and start updating the sh RoleBinding.yaml file. So I will write API version kind RoleBinding metadata name read hyphen pods. Now here under metadata I am giving a name to this role binding read pods. This name can be anything, but it should clearly describe what this role binding is doing. Now instead of spec, in role binding we define subjects. So what are subjects? Subjects basically define who we are giving access to. This could be a user, a group, or a service account. In our case, we are giving access to a user. So I will write hyphen kind user name intsch viewer and API group RBAC.authorization.kubernetes.io. Now let's understand this. Here kind user means we are binding a user. Name intsch viewer, this is the user we created earlier. API group is RBAC authorization.kubernetes.io. This tells Kubernetes that this user belongs to the RBAC API group. Now we need to attach a role to this user, and that is done using role ref. So I will write role ref kind role name sch pod reader and API group RBAC authorization kubernetes.io. Now this is very important. Here kind is role. We are referring to a role, not the cluster role. Name sch pod reader. This must exactly match the role we created earlier, that is sch pod reader. API group, same RBAC API group, that is RBAC authorization kubernetes.io. So this is our complete role binding manifest. So what is happening here? We are connecting user intsch viewer to a role, that is sch pod reader, and this connection is created using role binding. So in one simple line, role binding is nothing but attaching permissions to a user. Now I will save this file. Since I am maintaining everything in version control system, that is GitHub, so I will push this to GitHub using git add, git commit and a git push command. Now let's go back to the Kubernetes master node. First pull the latest changes using git pull command, and now apply the role binding using kubectl apply -f day18 RBAC sch RoleBinding.yaml. Hit enter. Here we are getting unsupported value user. It should be user caps. So let's correct this. Save the changes. Push the changes again. Pull the changes. Apply the role binding again using kubectl apply -f command. Now you can see RoleBinding.RBAC.authorization.kubernetes.io read pods created. That means our role binding is successfully created. Now the user intsch viewer is no longer a skeleton user. It now has permissions, specifically read access to pods. Now let's switch back to our user and actually test the access. First I will check the available context using kubectl config get context command, and here you can see right now we are still on admin context. So let's switch to our user using kubectl config use context and this context name, that is intsch viewer -kubernetes. Hit enter. You will see switched to context int sh viewer -kubernetes. Now we are acting as a int sh viewer user. Now let's try the same command again to access the pods using kubectl get pods command. And you can see now it works. We are able to list the pods successfully. So this confirms our role and the role binding is working perfectly. Now let's try something more. Let's try to create a pod kubectl run nginx --image nginx. And you will see an error. User int sh viewer is forbidden. Means cannot create a resource pods in the API group. Because in our role sch_role.yaml we only gave get list watch. We never gave create. So Kubernetes is doing exactly what we defined. Read access, not the write access. Now let's switch back to the admin. Using kubectl config use context command. Hit enter. Now we are back with full permissions. Let's create a new namespace using kubectl create ns command, and the namespace name is testns. Hit enter. Now inside this namespace, let's create a pod using kubectl run nginx --image nginx, and the namespace name is testns. Hit enter. Let's verify it using kubectl get pods -n test namespace. Pod is getting created. Now comes the important test. Let's go back to our limited user using kubectl config use context and then context name. And now try to list pods from that new namespace using kubectl get pods and then namespace name. Hit enter. Again, you will get forbidden error. Now this is a very important concept. Why did this happen? Because roles and role bindings are namespaced. That means the permissions we gave are only valid in the default namespace. They do not apply to the other namespaces like testns. So if you want the same access in multiple namespaces, you have to create role bindings in each namespace separately. Now think about real world scenarios. If you have 10 namespaces and 20 users, managing role binding in each namespace becomes very tedious. Also, some resources like persistent volumes, nodes are not even namespaced. So role binding cannot handle those cases. So naturally, a question comes, can we define permissions at a cluster level instead of namespace level? The answer is yes, using cluster role and a cluster role binding. Just remember this simple difference: role binding, namespace level access; cluster role binding, cluster wide access. We will deep dive into cluster role and cluster role binding in the next lecture. So in today's session, we learned how authentication and authorization work in Kubernetes, how to create users, define roles, and bind them using role binding to control access. If you found this helpful, don't forget to like, share with your friends, and subscribe to the channel. Thanks for watching and happy learning.